In this example, we're looking at a tapered rod. The rod is the length of L. And what we know is that the cross-sectional area of the rod varies in a linear way from the left side over to the right-hand side there at x equal to L. There's an axial load which is applied to the end. And what we want to know is what's the total axial elongation of the rod as a result of that load there, P. Okay, let's look at a cross-section at X. And what forces do we have which act? Well, if we make a cut through here, anywhere we cut, we're going to expose an axial load there at P. So in using our elongation equation, E is the integral of the axial load F as a function of X divided by the Young's modulus potentially as a function of X and the area as a function of X integrated over the length, 0 to L. Well, we can see here that as we integrate this over the length, the axial load F is going to be constant, and that comes out on the outside. We know that the material doesn't vary with X, so that's going to be something that comes out on the outside. So this is going to be the ratio of P divided by E with the integration of 1 over the cross-sectional area of A. It says that the cross-sectional area varies linearly with X. So let me write this as a linear function. It's the area A naught, which is what it is there at the wall. So the slope of this then will be A1 minus A naught divided by L times X. So that is our function of X. Just a shorthand notation is I'm going to call this A and then I'm going to call this B. So from here on out until I get to the end, I'm going to write that the area is equal to A plus BX. So therefore, our elongation is the integral 0 to L dx over A plus BX like this. That integration is going to be equal to the natural log of A plus BX with a 1 over B in front. So this is X equal to a 0, X equal to L. So what this does for us is it gives us the right-hand side, this is P over EB, log of A plus BL divided by A. So this becomes P over EB, natural log of A, which is A naught, plus B, which was equal to what? A1 minus A naught over L times L, divided by A, which was A naught, so this gives PL over E A1 minus A naught times the natural log of the area on the right-hand side divided by the area on the left-hand side. So this is just a very straightforward application of our elongation equation when we have non-constant properties along the rod. simply had to write the area as a function of x. We had to find how the load, the actual load, varied with x, and in this case it didn't. It was a constant. So it was just a matter of integrating 1 over the cross-sectional area A in order to get our elongation result.